So we talked about different types of ciphers. We talked about the Caesar cipher, in which in other replacement ciphers, where every letter is replaced with a different letter or replaced with a number or something like that. But the problem with those types of ciphers is that they're pretty easy to crack. Once, like for the Caesar cipher, once you figured out one kind of combination, the rest falls into place really easily. For other replacement ciphers, it's also not too bad once you get to a place where you can kind of figure out what that might be. So easier ones or harder ones that are used and harder to crack are a type of substitution cipher, at least kind of. But what it does is it doesn't actually replace every letter with the same. So in this case, they're not always the same from the coding to or from the actual message to the encoded message. So an E might be an F or something like that in a substitution cipher, but in these types of ciphers, an E is not always an F. And so that makes it kind of tricky because once you've decoded one letter, it doesn't mean that every other letter is going to be replaced with that same letter. So we're going to use a matrix to help that in that model. But first, we do have to know what and replace each letter with a number. And so this is just a standard alphabet. If you did do your Caesar cipher, you probably wrote it all on there too. So all these numbers on the outside or on the inside, it doesn't matter. You could use either one, are the numbers that we're going to use. And so let's say that your message was meet me at the mall. So we're going to replace every letter with a number as our first step. So we'll just look at each one and replace. So M is 13, E is 5, T is 20. M we already knew was 13. E was 5, A is 2, T is 20. We already found that. 20 again, 8, 5, 13, 1, and then L is 12 and 12. So far we haven't gotten to a place where it's hard to crack yet because, as you can see, every letter that we have is replaced by the same number. So that is the start of it. It's definitely replacing it in that way. But the next thing that we need is a keyword. So as you create your cipher, as you create your message, you need to have a keyword that you tell so-and-so that would help decode it. So let's say our keyword is fish. So fish only has 4 letters. So we're going to create 2 matrices, and it doesn't necessarily have to be 4 by 4. In this case, because it has 4 letters, it's going to be something by 4. So our columns are going to be 4, but the rows actually depends on what your message looks like. So ours actually are going to be 4 by 4s, but it doesn't necessarily have to be 4 by 4. It could be like 6 by 4. But the important part is that this keyword here determines how many columns we have. So 4 letters, so 4 columns. So our message and our keyword, keyword, are going to be 2 different matrices. So I'm going to make my keyword matrix now. And again, our keyword matrix has the columns across the top. So that's why we have 4 columns, because we have a 4-letter word. And we translate again these different letters with our numbers here. So F is 6, so we'll put 6 all the way down. And again, ours actually is only by 4, and you'll see why here in a second, but it could continue. We could have as many 6s as we want down the column. I is 9, so likewise, as many 9s as we want down the column, but again, ours is only by 4. And S is 19. H is 8. So as many as you need to actually fill your message. So now that we know that, and we know our keyword, we can put in our message. And again, we take all the numbers that we have here in order and go in rows. So 13, 5, 5, 20. Next row is 13, 5, 1, 20, 20, 8, 5, 13, and then, is that right? Did I miss one? Yeah, 1, 12, 12. And it is weird that we have like this blank here. So there's a couple ways that you can treat that. Because we had this unknown one, honestly, what we could do is just leave it. We could leave it blank. But sometimes what they do is they put in a new number to signify that you're either like dealing with a period or you're dealing with space or something. So for us, we're going to put in a dummy. So this is going to act as a dummy character or a number. And so ours is saying that like our dummy character is actually representing our period in our case. Not that we would necessarily know that, but once we decode it, like we'll see that it doesn't actually match up with anything, and so we can kind of know that it's not necessarily this extra letter that we're dealing with. So we've done both the message and the keyword. So our next step is to add the two matrices together. So again, adding matrices means we add piece by piece the corresponding placement. So our first row, first column is added to our first row, first column. So 13 plus 6 is 19. And we'd continue going. 5 and 9 is 14. And we would match up. We'd keep going down the column by column, row by row. So I'll just give you then, so that we don't have to spend a bunch of time adding up things. The resulting matrix. And so that means that the coded message is not represented obviously as a matrix, but we used our matrix to get there. So we'd put all these in a string of letters. So our coded matrix would look like this, or coded message. So a bunch of numbers that don't really mean a whole ton. Now, again, the important part for this is that to decode this, if I was just giving you this part, and if you used the methods that we learned before, you would think that this 14 and this 14 were the same character, but they're not necessarily the same character. Remember that in our original message, meet me at the mall, we had a double E here, which means that both these actually are E's. But there's no way to actually know that because they're appearing as different numbers, which, again, this is why this is a harder thing to crack, because you actually need this keyword. This keyword's important to get to our coded message, and if our keyword wasn't fish, for example, if it was, I don't know, back or something like that, we'd end up having a different coded message, and it would be even harder to crack. So in order to actually encode these things, you need to pass on the coded message as well as somehow indicate to the person that you're sending this message to what the keyword is so that they can actually crack it. So let's say that you are that person. Let's say that you do end up having a coded message that you need to decode. And so this is the message that you're getting from someone, and you do end up getting a keyword, and your keyword in this case is going to be virus. And so if I was trying to decode this message, we would do exactly the opposite that we just did. So what we resulted in is this coded message here. So how we got that is we added the message and the keyword together to get this resulting matrix. So if I'm working backwards to get the message, I know I added on the keyword matrix. So in order to work back here, I would have to subtract it off. So we're going to put this in our message that we end up getting into a matrix. But remember, because we have this keyword here of virus that has 5 letters, we're going to subtract then a matrix that's going to be a 5 column, since we have that 5 letter keyword. So we're going to have two matrices, and this is going to be our keyword of virus that we're going to subtract off of. And then we can put our coded message, again, with 5 columns here, and in with our rows. So 41, 29, 19, 46, 20. So that's 5, 42, 17. And again, this one was kind of the same as before. We actually ran out a little bit, and that's okay. We don't necessarily need this box here. It just means that we're ending our message, and it would be added to the S here, but or subtracted from the X, but it actually isn't really super important. So we're just going to leave that alone. Sometimes, too, there are dummy characters within the message, so it's possible that you end up getting here or something, that this space, even though I put a space here, it might mean that that is actually a character like 27 or something like that. And so they would say using 27 as a space or using an extra character as space or something like that. So know that that's a possibility too. But we're going to subtract off our keyword, which is, again, virus here. And we use our chart here in the corner to help us with that. So V is 22, so we'll continue that down as many rows as we need. I is 9. Same thing, and again, this ends up being a 5 by 5 again, but it doesn't have to be. It could be like a 6 by 5 or a 4 by 5. It's just as many as you need to continue with your message. Here's 19. So we're going to subtract our messages here, placement by placement. So 41 minus 22 is 19. 29 minus 9 is 20. And so on and so forth. 19 minus 18 is 1. So I'll give you again the resulting matrix so that we don't have to spend a ton of time with that, but we would just subtract piece by piece. And now what we're getting here is our original message where every number is represented by the same letter. So we can just use our chart backwards. Oops, there was nothing. Use our chart backwards to decode our message. So if we look in our chart, 19 should be S, 20 should be T, 1 should be A, and so on and so forth. So we can continue on. I'm just going to do it down here. So our first word, which was 4 letters, so we saw that up here, is stay. So our next word is A, T, because 20 is representing T. So that's like our second word. The next word that we had was 4 letters, so 8 is O, or H. 15 is O. 13 is M. 5 is E. 19 again is S. H, E. T. And so on. So we're here. So our next one is I. 14 is N. And then last word. Oops. Oh, that should be 16. Missed one. So again, knowing our original coded message was something that we couldn't actually decode until we knew the keyword. So if I picked a different word, what would end up here at the end is something that would be gibberish. So the importance here is that in our first row here, even though these 27s are all the same, they ended up being all different letters when we actually decoded our message. And so that extra layer of complexity there makes it harder to crack these codes. So the last part that we're going to look at today is a different type of coding model, and it's actually really, this is a simplified version, but it actually is really important to kind of understand this idea of binary coding because it's used in a lot of encryption methods to keep information that is pretty sensitive, keep that information really confidential. So credit cards are something that they use binary coding models to do that. And it's because we have a really cool, we have some information that we know about binary, and we have some interesting characteristics that go along with it. So we need 3 different facts to know this idea of addition of binary numbers that we use to encode these different numbers. So one of the facts is that 0 plus 0, and in this case it actually makes sense, it's just 0. 1 plus 1, again, also makes sense, it's 1. And 1 plus 1 is actually in binary, not 2, ends up being 0. Binary is only dealing with zeros and ones, so this is the only one that doesn't actually make a ton of sense to come up with our new binary coded model. So let's say that we have this binary number here, and we've already looked at binary numbers before. We've talked about how some of these binary strings can represent, like 1 can represent something that's like black, and 0 can represent something that's white. We use binary also to represent different numbers. So if I have this binary number and I have this binary number, and I want to add these 2 binary numbers, I'm going to stack them on top of each other, because it's definitely easier to see it that way. You kind of add like normal, place by place, but know again that like not everything makes a ton of sense. So 1 plus 1 again is not necessarily in our actual algebraic sense. It's 1 plus 1 is actually 0 in binary. So 0, 1 plus 0 is 1, 0 plus 1 is 1, or sorry, 0 plus, 1 is 1, 0 and 0 is 0, 1 and 1 again is 0, 0 and 1 is 1, and then 1 and 1 is 0. So this new code that we ended up getting, this is called the encoded binary string. So it's the encoding of like taking this message that we have, adding this kind of like a keyword, and we're getting this encoded number. So here's the reason why this is important, or why we use this over the internet. It's because if you add the same number twice to a given number, you get the same number back again, or the given number back again. So if I wanted to decode this string, so I encoded it right here, I got this coded model. If I wanted to decode it, so I'm going to start with that number, this was the coded message that we found in example 3, so 0, 1, 0, 0, 1, 1, 0. And I want to now decode this binary string. What I would do is I would add on, this was like the keyword, I want to add on that number that I added on in example 3 again. So 1, 1, 1, 0, 1, 0, 1. So again, same kind of facts, 0 and 1 is 1, 1 and 0 is 1, 1 and 1 is 0, 0, 1, 0, and 1. And so what we should end up getting here is the given number that we started with, which is right here, back again. And so this part is decoding the binary string. If I want to decode something, I would take the coded information and add on basically that keyword or key binary number, key binary string in order to get that. And so this is why this is important, or why we use this. What actually happens when you make some sort of purchase online is that you put in your credit card information. That credit card information is converted into some binary string like this, some set binary string that represents your credit card information. This merchant sends some random binary string to your computer. So whatever thing that you're actually purchasing from, it gets transferred to your computer. Your computer adds the two binary strings together and then sends that result to the merchant. The merchant adds that random string that they sent to you to your number to get your credit card. And so that makes it something that is more encrypted, because if someone were to intercept that random binary string somewhere, like while you're transferring that information from your computer to the merchant, if that were to get hacked, they would have your credit card information because it'd be really easy to decode. But because they sent this random binary string to you and added it to your credit card information, it ended up getting an encoded binary string. And without the key string that they added, without that random binary string available to them, they wouldn't be able to decode that. So this prevents your credit card from being intercepted because you don't know how they encoded that. You don't know the binary string, and you can't really work backwards very well to get there. So that's actually how your credit card purchases are made, and how they encrypt that information so that it keeps that information, that sensitive information, confidential. So kind of cool to know that, like, even though we're dealing with maybe some silly ideas here, like these matrix models and how they were maybe important way back when we were trying to give information or try to have information protected from different countries or something like that during war. It's actually important now. There's a lot of things that people do with encryption processes, and as you can probably, as you know already, that stuff is really important because people spend a lot of money and spend a lot of time trying to hack things so that they can get important information to sell. And those, we kind of want to stop those bad guys. So we want to come up with models that make it really hard to do that. So this is something that that happens when you actually do make these purchases online.